This meeting is being recorded.
Did it start recording properly? Yes. All right, cool. Okay. Hi, everybody. Okay. So quick notes before we get going. If you're working on project 2B still and you're having problems with auto-grader timing tests, I have two key tips. One, make sure you're not rebuilding the whole graph every time you call the hyperdems handle method. I did a bunch of these tickets like an hour and a half last night, and that's not super common. I'd say the most common error I was seeing was people iterating over the entire graph to find, for example, the vertices that go with a given word. So for example, if someone says transition, you shouldn't iterate over your entire graph. Do something faster. There's also issues I've seen where someone does retain all, contains, index of, etc. on a large array list. Try and use map, set, something else where you expect to get log time. But I'd say between these two top tips, you're likely to fix any of your issues. All right, moving on. Let's talk about today's topic, Quicksort. So this is gonna be our first Quicksort lecture. We're actually gonna do two on the single sorting algorithm because I love it so much. It's just a super cool sorting algorithm with some really cool properties. So before we get there, I wanna finish our discussion we had last time where we were trying to understand insertion sort. So if you did not digest insertion sort, hello. If you didn't digest insertion sort yet, sorry to say this question will be impossible for you, but everybody else, I'd like to pick up with that exercise we had at the very end of lecture last time. And if you answered it last time, feel free to answer it again. And the goal is to figure out what is the runtime of insertion sort, and give me a big omega and a big O bound, and give me the tightest bound you can. And here was the trace of how insertion sort behaved. So as a reminder, on this line, the idea is that what letter was the traveler on this line? E, I hear. And it went back 4 swaps. So we have 4 swaps on that line. Okay, so give it a shot, and then I will happily debrief in about 45 seconds. Okay, I'm going to spoil it very soon. All right, let's talk it through. So what would the very best case look like if you could describe it in terms of this diagram? Yeah. List is already sorted, in which case you'd have a green diagonal. What do you think the runtime would be in that case where the list is already sorted? In, right, because it'd be basically every item looks at its neighbor, it says, oh, I'm already in the right place. So the best case is theta n. And so I can represent that by saying, okay, well, I can bound it below by omega n. Okay. So the best case is theta n, so this is valid. That's the tightest bound. What about the runtime in the worst case? What would that look like? Well, I guess it would look like the green is always at the farthest left position, and all of these are filled in. So what's that runtime? Someone else in this quadrant of the universe. N squared, right? And the idea is it's the area of a triangle, or in this case, a right triangle. Okay. So correct answer is theta n, big O n squared. Okay. Now I kind of cheated here a little bit. You could have also technically said this answer and been correct, but then I would say you're being pedantic. Or not pedantic, but you're not using as tight a bound as you possibly could. So you could also say that it's omega 1, because surely it's at least constant time, but the tightest bound is omega n O n squared. Okay, so both of these are true. This one's more useful. Okay. All right. Some of you probably still feel a little uncomfortable with the distinction between best case, worst case, omega, theta, and big O. Totally normal. Hit those, A-level study guide problems, or argue with your friends about this. Why is it the case that both of these are correct and this one's better? Cool. All right, moving on though, not to get bogged down in asymptotic notation. Here we go. Got another problem for you. So let's suppose we have the following goal. So we read 1 million integers from a file into an array of length 1 million. I mean, maybe not all that distinct from project 2B. Not that that's part of the project, but you know what it's like to read a bunch of integers in. Suppose we then merge sort the integers. So they're all in order now. We've cut the array in half, all the magic happens, takes n log n time. And then let's say we select one integer randomly and change it to some other value. Like you just pick one in the middle and you change it to 1 billion or 6 or -32. And now I get to sort using algorithm X of your choice. Which of the following algorithms do you think would be fastest? And by fastest, I mean you run it and you see who gives you the best result. Okay? Like it takes the least amount of time to complete the task. Okay. So I'll let you answer this question. It's a little counterintuitive, but fun. So you get to pick X. I'm gonna wait for some more replies. Two more. Okay. All right. So somewhat counterintuitively, the correct answer, it turns out if you were to run the experiment, which you could do empirically, insertion sort would actually tend to be the fastest. Okay. So it turns out that D, despite being n squared, in the worst case, it's going to be the fastest algorithm. So why? Okay. This is a hard question. So I'll give you an example. Imagine you have an array which only has a small number of inversions. So for example, in this array, AEELMOBRXYZ, this is kind of an analog to the question I just asked. You know, there was some other letter here, but we swapped it out with B. We just changed one of the letters. When we do the swap, whenever we do the sort, the runtime to complete insertion sort is just however many swaps. So in this case, 5 swaps, and that's it. So compared to merge sort, which is going to split the array in half and do a bunch of divide and conquer type stuff, turns out insertion sorts is going to be super fast. Now you have to actually run the experiment to be fully convinced that that's true, meaning that this question was really mean. But it is interesting that even though it's an n-squared algorithm, in this specific case, where we're only taking some items and moving them back a little bit, there's not very much work to do. Now that's true not just in the exact case I described where one item's out of place. Could be that you have a number of different items that are out of place, but just by a little bit. So it turns out that for an array that's almost sorted, not well defined right now, insertion sort's going to be blindingly fast. Okay, cool, right? So it's like, yeah, it's bad at doing the general purpose job, but when the array is almost sorted, it's awesome. Any questions about that? Okay, so there's something that if you're feeling like a little shaky ground here, this is the picture, Bielmo. When you feel confused, think Bielmo, and then you're good, right? You know that in this case, we're just a single item's getting swapped backwards, and that should be pretty darn fast. All right, so it turns out insertion sort will be better, as noted. Okay, so in this specific case, if you actually were to look at the runtimes and big theta notation of this particular algorithm, selection sort's going to be n squared time, heap and merge sort will be n log n time, insertion sort will be n. Now you can tweak merge sort to make it a little faster. If you use tim sort from Python, I'm not going to talk about that here, such that it is actually also going to be theta n, but the merge sort we described is going to be n log n. Okay. Because it's going to create a bunch of auxiliary arrays and make a bunch of copies and all that stuff. Okay. What's the first step of heap sort, just as a reminder? So let's say you tried to heap sort this. What would happen? So it's almost sorted. You turn it into a max-oriented heap. What will be the front item after you heapify? Just kind of a review. Right? That's pretty bad. So if you heap sort an almost sorted array, you're going to basically undo all of the work that's already been done for you and then redo it all. Okay. So these algorithms, they're just going to do lots of extra work that's not necessary. Insertion sort's going to be fast. Okay. So more generally, on an array with a small number of inversions, remember an inversion is pairs of items that are out of sorted order. Insertion sort's going to be very fast. And so what will end up happening is it's going to be exactly one swap or one exchange per inversion. So, right. So here we had 1, 2, 3, 4, 5 swaps. Is that right? Yes. So we did 5 swaps. There were 5 inversions. That's exactly how many swaps we do. Okay. And then the number of comparisons is going to be number of swaps plus 1 per line. So it's about the same. So you can say the overall runtime is theta in plus k. The theta in is the cost it takes to basically say, traveler, it's your turn. And then k is the total number of swaps that happens. Okay. And so if we define an almost sorted array as one in which the number of inversions is less than or equal to c in, then insertion sort is going to run in this amount of time. Okay. And why do I say c in? I'm just saying it's some arbitrary linear function of n. Okay, so maybe it's 5n inversions or 80n inversions, doesn't really matter. As long as it's linear and n, then we call it almost sorted. Okay. So that's cool. Insertion sort, even though it's an n squared algorithm in the worst case, which was the first problem we did, because it's the area of that right triangle, in the special case where you're only swapping a small number of items, a small number of spaces, then it's going to be super fast. Another thing that's super interesting is that for small arrays, insertion sort will also be fastest regardless of the number of inversions. Now, this is something that's more of a empirically studied fact, like people run experiments on real computers with real data sets. We're not going to do any kind of theoretical analysis. If you want, you can look at Donald Knuth's Art of Computer Programming book, but really it's an empirical experimental problem. And the reason this is the case is that algorithms like merge sort or heap sort or quicksort, which we'll talk about soon, they spend too much of their effort doing the dividing and conquering, and they're not doing enough just full on conquering. Insertion sort gets straight to the point. There's only, if you only have 10 items, that's only 100 arbitrary units of work. It turns out to be faster than you'd get with merge sort. And so if we look at, for example, I'm not going to click it here, but if you look at the Java implementation of merge sort, you'll see that it does that. It has a special condition that says if the array I'm trying to sort right now is less than, or the piece of the array I'm trying to sort is less than some constant. I think in Java it's actually bigger, somewhere around 40. If it's less than 40, just use insertion sort. Okay, that's one of the kind of cool hacks that's out there. And if this gets your gears going, 61C might be a good class for you, learning how to write really performant code that is super clever. So I'm going to say this and then happy to take some questions. We've now seen 4 different sorts. We got the selection sort, the heap sort, which is a better version of selection sort that uses a heap to keep track of where the smallest item is. We have merge sort, which is extra clever way to split arrays in half over and over. And now we have insertion sort, which has the neat property that it's really good if the array is almost sorted or if it's small n. Okay. All right, any questions about this? Yeah.
Is there any way to sort an array without at least looking at like an array that hasn't already been looked at?
Question was, could we sort an array without looking at all the elements? The idea being, I want to beat that theta n runtime for almost sorted arrays or sorted arrays. I mean, you could always come up with a hack. Like if the array is sorted, you have a special flag that just says, I'm already sorted, please don't bother. But beyond that, no. I mean, you have to look at all the data to know. Yeah. Now, it's interesting to note that if you had a special purpose situation where you had a computer where you only ever, I don't know, some finite number of objects, you could build a piece of custom hardware that could like check if an array is sorted all at once, but that requires all of the array to be able to fit in memory all at once. So, yeah. Okay, so these are all of our sorting buddies. We've seen many different flavors. So now let's introduce the best buddy of them all, Quicksort. Okay. So Quicksort is a really interesting algorithm in that it was invented by not a computer scientist who was just dabbling, like basically a guy trying to figure something out. And he didn't have access to any resources out there. And so he just had to make up his own sort. He had no sorting library in the year 1960. Okay. So to set contrast to what this guy came up with, Tony Hoare, I'll tell you about him shortly. So the types of sorts we talked about so far are selection sort, which is about finding the smallest item, selecting it, putting it at the front. There's heap sort, which is just a variant of selection sort, where you use a heap to keep track of the smallest thing. Okay, so these are basically the same idea, just this one has a special data structure that makes it faster. We have merge sort, where it's all about merging two sorted arrays. We have insertion sort, which is figuring out where to insert the current item. And now we have Tony Hoare's idea. So in 1960, Tony Hoare was studying abroad in Moscow in the height of the Cold War days. And he was a novice programmer working on the problem of machine language translation. And he wanted to, and actually this is back in the golden era, one of the first golden eras of AI, where the sense was all of these really hard societal problems would be solved soon by AI, because now we have computers that could do things like automatic translation. So working on this project, Tony had to decide that he ran into a situation where he wanted to sort his data. Okay, so here's the idea is that, let's suppose we have a sentence like the cat wore a beautiful hat. Okay, those are the N words that he has in mind. Here's the cat. And in order to translate this into Russian, we have a dictionary of English words, where for some reason this is the cutesy word of the word cat if you speak Russian and so forth. And so the idea is, just crudely, if you wanted to have just a very baseline circa 1960 translation, then I'll just look up each word individually. Okay, and so I come up with perhaps some literal translation that's a little weird, but you know, someone would know roughly what I was saying if they spoke Russian. Okay, so how would I do that? Well, one way we would do it today is we would probably, given this array of sorted words, or I'm imagining it's just given as an array, we could binary search for each word. So we look for the word the, if such a thing even exists in Russian, and we would find that in log d time. We take cat, and that would take log d time, and so forth. And so for each of our n words, we'd have n log d time. Now, it might not be an array. It could also be a binary search tree or whatever else, but this would be one way you could do it, okay? A series of binary searches. Okay. Now, Tony Hoare had this interesting constraint in the year 1960, which is that you could not fit a dictionary into RAM at the time. There's just too many words. It's just no computer had enough memory. So that information was stored somewhere, but it was stored on tape. And by tape, I mean like a literal physical piece of tape, like magnetic tape that was large, and you would have to scan along the tape to find the words. So it was like an array, but stored on a piece of physical tape that you had to spool and unspool to find what you were looking for. Okay, not by hand, but a machine would manually, that would automatically like kind of go back and forth and scan this thing, okay? So doing n binary searches of d length, that's n log d, but that assumes that binary search is log time. But at the time, binary search was not log time, because if you wanted to actually scan a tape, you had to physically spool your way to the middle, then halfway over, and then halfway over, over and over, and you'd find that in that model of computation, where you have to physically move a tape, binary search is actually linear time. So it's kind of slow, okay? So as a result, because we can't access arbitrary memory locations in log time, he had to do something else. So his approach, this is just Tony's idea in 1960, is, well, the sentence fits in memory. Like the cat had a nice hat, that's fine. That fits in memory. So he'll sort that, and with modern sorting technology that takes n log n time, where that's going to be very small, and then we just scan through the tape once. So that is, I have the cat wore a beautiful hat. And so we'll just scan through this thing. Once I've sorted that sentence, I'll find A, and then I'll go through and find cat, and so forth. And so I'm just going to go through the tape exactly once using my sorted sentence. And so the exact details don't matter too much, but the idea is he wanted to be able to sort sentences. And he had to do it without any kind of sorting library in his programming language. There was no Google. He just had to make up sorting. And so the idea he came up with to sort was based on not selection, not based on merge sort, not based on insertion sort, but instead partitioning. And this is just the weirdest idea that anybody ever had, but it turns out to work out pretty well in practice, though not at the time he invented it. All right. So here the idea is, what does it mean to partition an array? So what Tony was thinking was, okay, I'm going to pick an item, which I'll call the pivot, and then I'm going to rearrange everything so that all the small items are on the left and all the large items are on the right. Tony, I should know, was a mathematician. That was one of his main areas of interest. So I don't know, more natural to him than maybe other people. And so to partition an array, the idea is that if this is my pivot, so item AI, then I'm going to move X to some position J. I don't know where that is, right? It's going to land somewhere arbitrarily. And all the items to the left are going to be less than X. And all the items to the right are going to be greater than X. And I lied, actually, sorry. It's that all the items to the left are less than or equal to X. and all the items on the right are greater than or equal to X. Okay. So what I'd like you to do is, given that definition of partition, I just want to see if it makes sense, because you have to understand this for the rest of the lecture to make sense. So tell me, among these 4 potential partitions, A, B, C, and D, which ones are valid? Which ones obey this definition? Okay. So I'm going to give you guys a minute and change to think about this. And this time the word is take instead of make. And by the way, that's the first time they've ever rhymed. So that's a good omen for today. And based on the fact that it's a checkbox question, multiple may be correct. Okay. Just a tiny bit more time, because I really want everyone to actually at least think about it, even if you don't answer it. Okay, so turns out that A, B, and C are all valid partitions and D is not. So A is fine. All the items to the left are less than or equal to 10. All these are greater than or equal to 10, the pivot, the green 10. Over here, all these are less than or equal to. And yeah, it's the case that 10's over here and 4's here, but that's totally fine. That's allowed by the rules. This one's not good because there is an item to the right of the pivot that is bigger, and this one's fine. Right? Any questions about the definition of partitioning? Okay, so how do you partition? That's going to be my next question. So this is the kind of question you might get asked at a job interview. Someone comes up with some clever little problem. And so I'm going to give it in terms of colors, because I think it's easier to think about the problem that way, but you may not receive that guidance. So given an array of colors where the 0th element is white and the remaining items are red or blue, rearrange the array so that all the red squares are to the left of the white square and all the blue squares are to the right. And your algorithm has to finish in n time, and I have no constraints on the amount of space you use. And I don't care about the relative orders. These are both, for example, valid outputs. So I'm going to give you guys about 2 minutes to think about this problem, then I'll take some suggestions. Maybe only 1 minute. And as you know, you can also think of it as numbers which are less than or greater than the leftmost item. Okay, I'm gonna take some suggestions. All right. What do you want to do? Anybody want to suggest an algorithm for doing this? Go for it. So are you creating a separate list? When you say add to the end of the list, it's already in the list. So it's written literally, this would result in duplicates. So yeah. What do you do slightly differently? You have a separate list? Okay. Okay. Sorry. Create a new list. Traverse the old list. As you see items, add to beginning or end of the new list as appropriate. Something like that, right? Yeah, this is the most straightforward approach. I think it's quite natural. Let's see it real quick in action. So I create a new list. I'm just gonna do it without colors. So we traverse the old list. 8, as you said, goes at the end, right? Because that's bigger. 3 is gonna go at the beginning. Then 1's gonna go at the beginning. Then 2. Then where does 7 go? At the end, I guess. 7. And then 4 goes here. So you could use add last, add first operations, and then at the end you add 6, I suppose, right? So you end up with that output. Okay, so yeah, very easy to do with a deck data structure. Okay. Big items get add lasted. Yeah, add firsted. Oh, right. Okay, good point. I don't want 6 at that position, so I want 6 to be in the middle. So then what do? Good point. You got to tweak the algorithm, which I messed up.
I think it's easier to do it with just like a plain array.
Yeah. Oh, we could do it with a yeah, with a plain or yeah. So there's a caveat here.
Starting from the right hand side and put the small items in starting from the left hand side.
Right. Yeah. So very similar algorithm. Yeah, I see. Yes. With array, you can put the 6 in the right place more naturally. And I put words in your mouth. You didn't say a deck. I did. Okay. All right. Yeah. So I think using an array, there's a more natural approach. And in your approach, you'd end up with 8, 7, I think, right? Or 7, 8 rather. Yeah. Okay. All right. So let's see. Let me just do that process again. I'll get rid of this one. So this is my input. Now using an array as opposed to a deck, because I was trying to be too clever. You would basically get 8, 7 over here, or 8. Then 3, 1, 2. Then you would do 7. Then you do 4, and then you do 6, something like that. Yeah, seems great. Okay. I'm going to accept that as the official class solution. It is also the most natural. Yeah, it's pretty straightforward, I think. Just go through the array and fill in things where they need to go. There are other approaches, and I'll talk about one next lecture that's more efficient, but that's what we're going to go with for today. Okay. So the net result is that our approach is going to end up giving us 3, 1, 2, 4, 6, 8, 7. This is the kind of output we're going to see today. All right. So Quicksort. How to use partitioning as a sorting tool. Now that we know how to partition, what do we do next? All right. So here's the idea. Suppose I have the array 5, 3, 2, 1, 7, 8, 4, 6, and I partition it on that leftmost item arbitrarily. What ends up happening is we get the array 3, 2, 1, 4, 5, 7, 8, 6. How did I get that? I scanned through the array and filled in the items as you described, and we end up with this array. Okay. Now here's the really important point. There's 2 really important observations. One of them is that when we finish this process, okay, so this one of the observations is that 5 is in the appropriate place. In other words, it's exactly where it will be when the array is eventually sorted. Okay, hopefully you all agree with that. Everything over here is to the left, is all the smaller things, and everything over here is greater. So this is the right spot. You know, there's 4 smaller items and 3 bigger items. So you better be in this spot. Okay. The other super important observation, maybe you feel it coming, is that the 2 halves of the problem are now separate. There's no way that anything over here is ever going to end up on the right side. 3, 2, 1, and 4 all less than 5. So they can't possibly end up over here. And likewise over here. So 5 is in place, and it is a barrier between 2 universes that never need to interact again. So we can sort those 2 halves now separately. We could do that with, I don't know, we could insertion sort both halves or merge sort both halves, or we could do something like what we just did and do like a recursive process of what we've been describing. Okay. So if we do that, let's say we use partitioning again, we would say, hey, leftmost item, I'm going to partition on you. I don't know where you're going to end up, right? That's what's really fun to me about Quicksort. You have a big ass array, you pick an item, and you're like, where are you going to go? Ah, okay, you ended up in your right spot, and everything else gets tossed to the left and the right. Okay. So we got 3, 2, 1, 4, and then 5, which is the barrier between the 2 universes, represented twice here for visual clarity. And after we partition this, what will we end up with here? What will 3, 2, 1, 4 turn into? 2, 1, 3, 4. Okay. And over here, we'd end up with 6, 7, 8. Okay. And by the way, the fact that I had 2, 1 here is just based on the specific partitioning algorithm that you described. Different partitioning algorithms may not have that same order. To be a valid partition, all that we need is that these 2 items are less than or equal to 3. Okay, any questions about the process so far? Yeah.
What if the term that we're pivoting on is
Right. So if the item we're pivoting on is the minimum or the max, then we're only going to end up with one subproblem, which is going to be like basically imagine that you pick 8 as your pivot, or say this was 19 or something. It'll end up at the end, and we'll only then recursively sort just like one side, which is everything. Yeah. Yeah. We haven't decided how we're going to pick the pivot. I just picked the leftmost for visual clarity, or like actually just for a bit laziness. But it does make for nicer figures. All right. So then what does Quicksort behave like? Okay, let's actually do a full demo of how Quicksort feels. So we actually have a full algorithm here. But here I'm going to do a mostly full demo. Okay, so we initially have an unsorted array. It's the same one we were using with insertion sort, heap sort, and so forth, so you can compare them later. So we're going to partition on the leftmost item. So I'm going to first call partition 32. Okay. Now, when I do that, we can now color all the boxes to fit that nice little interview problem we had earlier. Red is smaller, blue is bigger, and white is the same. Okay. So 32 is going to end up right there after you do the partitioning procedure. And these are all the items that are less than or equal to 32. And because I'm using the partitioning procedure we described earlier, they're in the same relative order. That was one of the features of that process. Okay, so 32 is in its place. We have one problem, which is all the items which are less than or equal to 32, and then a right problem, which is all the items that are greater than or equal to 32. And you might notice I said all of these, so not exactly, but all the items over here are definitely less than or equal to 32. All right, so we're done with 32. And now we're going to quick sort the left half. And I'm not going to go through all the steps because it's just a recursive algorithm. I think at the very end of the slides, I have a more unrolled version. But you think about it this way. When we call partition 32, on the left side, the next thing we call is, actually, I should say, if we use the leftmost item, what's the next partition operation going to be? Partition of 15. It turns out that if you partition on 15, that's going to have a left problem, which is partition 2, and a right, which is partition 17. Okay. Partition 17, when you partition that one, there's going to be nothing less than or equal to after you do the operation. You can do it later if you want. The right will be partition 19, and so forth. And so this is the sequence of all the partition calls that get made to handle that left side. I didn't show them to you, and this tree should not be obvious to you, though those of you who are looking very closely may notice something interesting. But this right here is the left side problem. And then the right half is just going to be this partition on 41. Okay. Now if you don't really trust the recursion, I have a longer, more unrolled version that shows the whole thing, but I'm not going to do it in lecture. But if you want to see it, it exists. Okay. All right. By popular demand in the past. All right. So this approach is a nice algorithm. It works. And the basic idea is every time you call partition, that item goes in its place. So if I call partition on every single item in the array exactly once, we know the array will be sorted because partition gets a thing in its place. If I tell you, you go home, 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 I do that until I point at everybody. Once I point at everybody, you're all home. That's the argument. Okay. So it clearly works. Now, here's the other crazy thing about Quicksort. So Tony Hoare came up with this idea. In fact, actually, if you read the original document, which I should link somewhere, he originally came up with bubble sort, but he's like, I think that's going to be too slow. And so then he came up with this other idea, partition sort. And he just decided, I'm going to name this Quicksort because it's faster than the bad thing I came up with. But amazingly, it just ended up being faster than any other sort. Like it's still the fastest sort basically for sorting data. If you really, really, really care about speed and you don't care about other properties such as stability, which we'll talk about Monday, then Quicksort's the way to go. Okay? So in most common situations, empirically, and it's very difficult to show this theoretically, Donald Knuth, again, he tries in his book, but it's really an empirical fact. You have to just try it out on a bunch of data. And it turns out that he was right. It actually is quick. So good job, Tony Hoare. And for that, by the way, Tony Hoare, and because of this and many other things he's done, he was knighted by the Queen, rest in peace, and was, I guess, the only person I know who was knighted for computer science. I'm sure many others have been since. Not myself, though, and I'm not eligible as far as I know. Anyway, so how fast is Quicksort? Okay, well, that's another important thing. I've said it's fast, but if we wanted to actually do some kind of asymptotic analysis, then we need to do some work. We need to count the number and the difficulty, for example, of our partition operations. Okay. So as a rough picture, a theoretical analysis, so partitioning is going to cost theta k time, where K is the number of elements being partitioned. And that's what we saw in that job interview question, right? The time it will take to take your array and reorder it so that the pivoted item is in the middle and all the left thing less and equal to things are on the left and greater than or equal to things are on the right. That's going to be K time, where K is the number of items being considered. It's not 100% obvious, but it's kind of close. And so the interesting twist is that the overall runtime, already some of you are sensing it, it's going to depend on where the pivot ends up. Okay, so it's theta K per partition operation, where K is the number of active items. But then the overall runtime will depend on where the pivot lands. All right, any questions about this so far before we do this last little bit of analysis? All right. So let's talk about the runtime of Quicksort. So let's talk about the very best thing that could possibly happen to you. You have an array and I say, pivot, you go home. And home happens to be dead in the middle of the array. That is the best thing that can happen because now we've split our universe into two pieces of equal size, or very close to equal size, maybe off by one. Now, if these pivots also happen to land in exactly their middles, now the problem is split into 4 pieces. And then we split into yet more half pieces. And then we're done, right? At this point, we're done. I guess you can also call the trivial partition operation on the size 1 arrays. Depends on how you want to talk about implementing it. But you end up with this as your answer. Okay, so we're basically done at this point. That's very fast. Okay, how fast? Good question. What do you think? So this is the best case. What does this runtime feel like to you? Yeah. Log n? I mean, not quite log n. It's not, you want to be log, if it was only log n, that would mean you somehow avoided looking at all the items. N log n is a good feeling. Okay, yeah. N log n is the right answer. And if you want to be a little more, somewhat more formal, the argument is this, okay? So the total work at each level, the first partition, it's one partition operation that takes n work, okay? K is equal to n. We partition everything. Then we have 2 subproblems of size n over 2. So the overall runtime is going to be n over 2 plus n over 2. It's off by 1. So I'm putting double tildes to cover my ass a little bit. And I'm just swearing a lot today. What the heck? Shouldn't have drunk all that whiskey before lecture. I didn't drink a bunch of whiskey. Anyway, then we have n over 4 times 4. We have n over 4 operations that we need to do in each of these partitions. Wait, let me try that again. We have 4 subproblems, each of size n over 4. So it's n. And so the overall runtime is going to be n at each level. And there are log n levels. So overall, it's n log n. All right. Worst case. Well, the worst case would be the state or the situation you observed earlier. Given an item, it either ends up at the very end or maybe the very beginning. And so in that case, this would be the pattern. The pivot goes there, and then we do a subproblem of size 5 and so forth. What's the runtime here? So I'm going to give you less time. Yeah. N squared. 6 plus 5 plus 4 plus 3 plus 2 plus 1. Okay. So the overall runtime is going to be n squared. So that makes Quicksort a very interesting algorithm. In the best case, it's n log n. In the worst case, it's n squared. And it seems like, shouldn't merge sort just be better? Like merge sort's safe. So is heap sort. They're both n log n. This one has this weird corner case where it can go n squared on us. Okay. So the theory tells us that in the best case, it's n log n versus n squared. And the problem potentially here is that n squared is vastly worse. N squared causes the autograder to time out. It causes you to post on EdStim. It seems like my code's not working. N log n will not do that to you, okay? So how is it that Quicksort's the fastest? Why does Tony Hoare get a knighthood when his lousy algorithm is n squared in the worst case? Well, the answer is that on average, it's n log n. Now, if we wanted to do a rigorous proof, we need to use probability theory and calculus. I'm not gonna do that. 170 might. I can happily point you to a reference if you want. But the intuition that I'm going to give you in a little bit of empirical analysis will hopefully convince you that it is actually n log n on average. So here's my kind of hokey proof. This is not a proof, but it is a flavor of the correct proof. So let's imagine the 10% case. So in this case, we're pretty unlucky in that the pivot is always going to end up in the first 10%. This is not to scale, but the idea is like, here's the pivot and ends up there. Okay, that's not a great place for the pivot to land. It's not a terrible place. Like, not moving would be the worst. But in your case, we don't, in the 10% case, we land not that far from the tree where we started. Okay. Now we have 2 subproblems. And one of the problems is size n over 10, but one of them is still quite large, 9n over 10. Now, if we repeat that process again, and we get the exact same situation happening to us again, where the pivot lands in the 10th percentile roughly, then we'd end up with, on the left side, two subproblems. One of size n over 100, that one's pretty easy. Then a 9n over 100. What's going to be here? If it's also 10%. So how big is this, basically? So this one's n over 100. This is 9n over 100. How big will this be? 9n over 100. And then this one will be 81, right? So those are my four subproblems. Okay. Now, the work at each level is still n, right? N, and so forth. And so the overall runtime will be n times h. The question is, what is the height of this tree? So what's funny about this tree, if you think about it, let's say there's only, I don't know, 87 items, then this one's going to be null. There's no problem here. So there's going to be basically a long spine on the right where the problems keep going. And then the left side's going to peter out more quickly because we're eventually going to get to size 1 or less than 1. There's nothing to do. But over here, this is going to be basically the critical path, whatever this long right branch is. So the question is, if we keep multiplying by 9/10, how many times do you have to multiply by 9/10 to get down to 1? Well, that's going to be log base 10/9. Turns out that log base 10/9 is just change of base. It's a constant factor. So the overall number of levels is still log n, even if the base is worse. Okay. So the overall runtime, even in this kind of baddish case, is still n log n. Okay. This is the intuition behind the full proof. The full proof takes maybe 20 minutes and it requires things you don't know how to do yet. But again, happy to ship you over to Bob Sedgwick doing a video on it if you'd like. Okay. So the punchline here is that even if you're unlucky enough that the pivot never lands anywhere in the middle, as long as you're at least lucky enough that you're 10% of the way from the front or better, then the runtime's still going to be n log n. This is actually very, like the math is the same, in fact, as the rescaling of arrays. So with rescaling arrays, if you use an arithmetic rescaling factor, like you always add 2 extra buckets, or sorry, 2 extra array entries, or 50 extra array entries, or 100 extra array entries, the overall runtime for array deck or array list operations will be n squared. But if you do any amount of geometric resizing, that is, you increase your array by 10% or 1% or whatever, it will end up being on average linear time. So it's a very similar flavor here. Okay. Here's the other argument. Quicksort is binary search tree sort. Okay. So what does it mean by that? Well, heap sort, recall, was take all your items, insert them into a heap, delete them all out. Now you sorted your items. Okay. Quicksort, it turns out, in disguise, unbeknownst to Tony Hoare, who was not thinking about binary search trees, maybe had never heard of them. Turns out that his algorithm is the same as insert all of your items into a binary search tree and then do an in-order traversal. Okay. Now what? Why? Okay, here's why. So this is what Quicksort does, right? We partition on 5, we split the universe into 2 pieces, then we partition on 3 and 7. Imagine instead we insert all of our items into a binary search tree. Okay, the first thing that gets inserted is 5, that's the root. Then we insert 3, which goes over here. So what 2 items got compared? 5 and 3. Okay, well, that's the same thing you're doing when you're doing a partition operation. Okay, great, done. So that's one comparison that got made between 5 and 3. Okay, next up comes 2. We insert 2 into this binary search tree. Okay, so what gets compared? 5 gets compared to 3 and 2. And if you think about 2's journey as it goes through the Quicksort algorithm, it's the same set of comparisons. So when you partition this top array, do 5 and 2 get compared? Yeah, of course, that's how you decide where it goes. Okay, and then 2 doesn't get compared to any of these other numbers. The process of partitioning on 5 is, hey, 3, where are you compared to 5? Hey, 2, where are you compared to 5? Hey, 1, how are you compared to 5? And so forth. And then when you partition on this 3, you again are comparing all of these to 3. So 2, what are you compared to 3? Okay, I'm smaller, I go here. And at that point, there's no other comparisons that 2 gets subjected to. Okay. Now 1, when it gets inserted, same thing. 5 gets compared against 3, gets compared against 2. And then eventually you can think of this process of the 1 appearing, that's basically the partition on 2. Okay. So if you really want to convince yourself that this is fully true, the sequence of comparisons that are used to build this binary search tree are exactly the same comparisons that are made when you run Quicksort. So if you were to write out, you write Quicksort and you have a print statement every time there's a comparison, and you do the same thing with a binary search tree construction algorithm, you'll see the exact same print statements, not necessarily in the same order, but you'll see the exact same print state, same exact comparisons. Okay, right. So because of the fact that random insertion into a binary search tree takes n log n time, it is also the case that on average, Quicksort is going to be n log n time. And as it happens, they have the exact same best and worst cases because they are the same thing. Okay, pretty cool. This is why I like Quicksort. It is just like marvelously, it's like mind-bogglingly beautiful. So good. Okay. Now you can actually do some empirical analysis and determine what is the distribution of runtime. So this is Bob Sedgwick, who was one, the inventor of the red-black tree, and two, he wrote his PhD thesis on Quicksort, which is a really good read, in which he basically tries to understand Quicksort down to the, its bones, right? Because at that point, this is like the mid 70s, Quicksort was used. He wanted to really understand its properties. So he did some experiments and he found on old computers, because this is what it was possible to do, that the distribution of runtime of compare counts looks roughly like this. So if I take 1,000 items and I insert them into a binary search tree, or equivalently, I take 1,000 items and I quicksort them, the number of comparisons that are made looks roughly like this. Sometimes you get really lucky and it only takes 11,000 compares. This is that very best case. Sometimes you get unlucky and it takes 16,000. And sometimes you get supremely unlucky and it takes, takes about 1 million compares, okay? But that's so far over on this distribution that you should be more worried about quantum teleporting through the floor and suffering death from, I don't know, whatever's below the ground, right? Getting sucked into the lava below the earth might be more likely. Actually, anybody who's a physicist, I want you to work it out for me. Like quantum teleporting into the earth versus getting so unlucky with Quicksort. You're in the worst case from a random permutation, but I think it works out in Quicksort's favor. On average, the average number of compares is 2n natural log n. And again, that's a Sedgwick thesis question. And you can also compute the standard deviation of that number of distributions. But it looks like this. Okay? It's a cool distribution. All right. So to summarize Quicksort, all right, in the best case, n log n. In the worst case, n squared. And in the randomly chosen case, it's n log n expected because this is the distribution, and you're not going to end up in this n squared case. Compared to merge sort, which has n log n best case and worst case, yeah, it's a little dangerous, but it turns out it's faster. And again, there's no obvious reason why it is the case, but it is faster. Okay. So these are the sorts we've seen so far. And so the last thing I want to talk about, just to set the stage, I'm going to let you go, is the performance of Quicksort depends on how you pick your pivot, how you partition, and other things you might do to speed things up. So the question I want you to think about as you're waiting, this is going to be on Monday, by the way. Friday, we're talking software engineering. But on Monday is to think about what should you do to avoid the worst case behavior if you really, really want to be sure you don't run into it. Okay, that's it for today. And yeah, I hope you enjoyed Quicksort Journey Day 1.
Hi. My favorite topic. I never learned to be a secret.
Oh, yeah.
Yeah.
This is also, if I were judging a potential function, I would have them teach Quicksort. I would see what they know and don't know, and if they teach me. Keep the tone of work. I guess. Yeah. Then you go to the pivot strategy. Yeah, you shouldn't teach that in the first. Not the idea behind. Anyway, it's pro tip.
Yeah, okay.
Oh, hey, everybody. Okay. All right. Bye, everyone. Hope that was